In this part, we will now introduce forward rate agreements and interest rate futures. Both contracts allow you to lock in rates today for loans on future time intervals. The rate that you lock in today is what is called the forward rate in case of the forward rate agreement, and in case of the interest rate futures, it is called the futures rate. We will relate futures rates and forward rates. A forward rate agreement, FRA, at calendar date small t is specified by a future period T0, T1, with lengths that we denote by delta, a fixed rate K, and a notional N. At T1, the holder of the forward rate agreement pays a fixed rate K on the notional and in turn receives the floating rate on the notional. This is called floating because this rate is only known at the future time point T0. This forward rate agreement allows you to lock in a fixed rate today over the future period T0, T1. Suppose you know you're going to take a loan with notional N at time T0. According to then prevailing market conditions, you would have to pay back the loan along with the simple rate L T0, T1. Suppose you dislike the uncertainty of this interest cash flow today, and instead you want to lock in a rate K that is fixed today that you're going to pay on this loan. Holding this forward rate agreement does exactly that. Remember that you will have to pay the fixed rate K and you will receive the floating. As you now can see, the floating payments simply cancel off, and what you are in fact paying is the fixed rate K. Now, of course, the question arises, what is a fair fixed rate K that you would fix today given the market information that is all the zero coupon bond prices at small t? To answer this question, we now compute the value of this forward rate agreement and set it equal to 0. We start by the payoff of the forward rate agreement at T1. Remember, it is given by the difference of the floating rate payment minus the fixed rate payment on the notional N. We now re-express this simple rate in terms of the T1 bond price at T0. We will then call this I1 minus I2, and we will value these components I1 and I2 separately using discount bonds. I1 is a cash flow that we do not know today at time small t, but we know it at time T0. Hence, the value of this cash flow I1 at time T1 at time T0 is given by simply multiplying it with the T1 bond price. But since I1 is the reciprocal of the T1 bond price, we get as value at time T0 1, so that the time small t value is the T0 bond price. Now the time small t value of I2 we get even simpler because this is a cash flow that we know at time small t, hence its small time t value is simply given by multiplying it with the T1 bond. This is what we get. So the total time small t value of the forward rate agreement therefore is given by the difference of these two expressions that we have here on the right hand side, and we call the value VFRA. So we see the value of the forward rate agreement depends on the choice of the fixed rate K. The larger K is, the smaller is the value. It can even be negative from the point of view of the holder of the forward rate agreement. But of course there's a counterparty to the forward rate agreement, and for the counterparty the value will just have the opposite sign. So it's a reasonable choice to choose K, the fixed rate, such that the value is 0. Simple algebra shows that the rate K, which renders this value equal to 0, is given by this expression here. We call it the simple forward rate prevailing at time small t. When the time small t coincides with the initial date t0 of the loan period, we get back the simple rate L, which we now sometimes also call simple spot rate, just to highlight the difference to the forward rate. It's further an easy exercise to see that we can re-express the time t value of the forward rate agreement in terms of the forward rate as follows. Now this expression nicely shows again that there is a fair choice of the fixed rate K, namely the forward rate, which renders this value of the forward rate agreement 0. If K is chosen too large, the value will become negative. If K is chosen too small, the value becomes positive. Now think of the following situation, that K is yesterday's forward rate. Now yesterday's forward rate in general will be different from today's forward rate. That means if you entered a forward rate agreement yesterday at yesterday's prevailing forward rate, seen from today's point of view, the value may have become non-zero. It may have become positive in case the interest rates went up, but it may also have become negative in case the interest rates have gone down. If we let the length of the lending period converge to 0, that is, if we let T1 converge to T0, in the limit we obtain what we call the instantaneous forward rate with maturity T0. Elementary calculus shows you that this limit is given by minus the logarithmic derivative of the T-bond price with respect to maturity. Because the terminal value of the T-bond is 1, this relation is equivalent to this formula. The nice thing about instantaneous forward rates is that knowing all the instantaneous forward rates is equivalent to knowing all the T-bond prices. As before, for varying maturities, we obtain a term structure of rates. In this case, it's the term structure of forward rates prevailing at calendar date small t. This is also called the forward curve. It's easy to see that forward rates are related to yields in this way. That means that the yield is the time average of forward rates. It also follows from this relation that the short ends of the forward curve and of the yield curve coincide and are equal to the short rate. Similar to a forward rate agreement, an interest rate futures contract allows to manage the exposure to the future spot interest rate prevailing over a future period T0, T1. In contrast to forward rate agreements, however, interest rate futures are daily mark to market or resettled. To understand what this means, recall that the value of a forward rate agreement may change in time. At time small t, when you enter the forward rate agreement, you will do it typically at conditions which render its value equal to 0. But already the next day, economic conditions may have changed and the value of the forward rate agreement turns out to your favor to become positive. This value may, of course, also become negative. Eventually, it will converge to the payoff of the forward rate agreement. Now, instead of sitting and waiting and see the exposure to your counterparty getting positive value or negative value, market participants prefer to settle any change in value immediately. This is done by marking to market. In this example, it would mean on the day after today, you would settle this increase of value by receiving a cash flow from your counterparty, making the exposure to your counterparty again 0, while the next day you may have to return a part of that to your counterparty, and so on and so forth. Formally, the marking to market of interest rate futures contracts works as follows. At any calendar date small t, a so-called futures price is quoted. This futures price is related to the futures rates in this way. This expression looks different than the value of a forward rate agreement, but in effect, it reacts the same way to changing interest rate environment. The day after today, one determines the futures price, and the difference of the futures price on t plus delta t minus the futures price from yesterday is the cash flow to the holder of the futures contract. Recall, this cash flow can be positive or negative. The futures rate here is chosen such that the following two conditions hold. At the settlement date or delivery date of the futures contract, T0, the futures rate equals the underlying spot rate. At any earlier date, the present value of the cash flow in the future from holding the futures contract has to be equal to 0. These rules fix the futures rate, but there is no direct functional relationship between futures rates and zero coupon bonds, as is the case for forward rates. As a consequence, futures rates are generally different from forward rates. The difference of futures rates minus forward rates is called convexity adjustment. This difference is typically positive. As a market example, I mention here the Eurodollar futures contract, which is tied to the LIBOR. It was introduced by the Chicago Mercantile Exchange in 1981 and has been traded since then on that exchange. It is designed to protect the owner from fluctuations in future 3-month LIBOR rates. These futures contracts are highly standardized. Their settlement or delivery months are in March, June, September, and December. This is in contrast to forward rate agreements, which are traded over the counter.